In this lesson, we'll look at Newton's law of cooling. Example: the rate at which a body cools in air is proportional to the difference between its temperature T and the constant temperature A of the surrounding air. This can be expressed by the differential equation dt over dt, where the top dt refers to the temperature, the bottom dt referring to time, and that equals K times T minus A for some constant K. Part A, we need to show that T equals A plus BE to the KT, where B is a constant, is a solution of the equation. And in Part B, we'll have an example to work through. The solution then to Part A, let's write down the equation firstly. T equals A plus BE to the KT. And the first thing we'll do is actually write BE to the KT as the subject. So we'll write that firstly, take the A over, and it'll be minus A. So we'll get that it equals T minus A. Now we're trying to prove this result. So dt over dt. Now the derivative of that, well, firstly the A is a constant. The derivative is nothing. The derivative of BE to the KT, the exponential, well, we look at the index KT. The derivative of that is K. Let's write that down firstly. Then we multiply by that term BE to the KT. So what have we got? We've got the K firstly, and then BE to the KT. Well, above that we've just rewritten that as T minus A. So let's replace that with T minus A, and the result we have now is exactly what we were after. So we write as required. Terrific. Part B now, well, we'll need a little bit of space, so let's clear some room there. Now the A, recall what the A is. It says the air temperature around the body is 18 degrees Celsius. So that's what A is, okay? A was the temperature of the surrounding air. Now it says that the heated body cools from 70 degrees Celsius, okay? So that's the starting point. So when T is 0, when time is 0, the temperature is 70 degrees. And then it changes to 35 degrees in 4 hours. So when time is 4, the temperature is 35. So writing our formula down, where A equals 18, we have T equals 18 plus BE to the KT. And applying our conditions there, when T is 0, our temperature is 70. So let's write that. Equals 18 plus BE to the 0. And then we get that 70 equals 18 plus B, where BE to the 0, of course, simply is B. And that equation there, taking the 18 over, we then get that B equals 52. Now, we've got the equation, we've found that B, which is a constant, equals 52, so let's rewrite the equation. If you like, we're updating it with our information we've found. Let's put a box around that. The other condition is when T equals 4. So when T is 4, the temperature is 35. And we've got 18 plus 52 e to the KT, where of course we'll replace the T with 4. Now that 18, we can take that to the other side, subtract it, we get that 17 equals 52 e to the 4k. And we're trying to get that e term by itself. Let's divide through by 52. Okay, we'll do the 52 e to the 4k firstly, so we're going to get e to the 4k, and it equals 17 over 52. Now, getting rid of that e, we need to take the log of it. So we'll take the logs of both sides. We get, on the left side, take the log, get rid of the e. We get 4k, and it equals the log of 17 over 52. Trying to get k by itself, so let's divide through by 4. We get, therefore, that k equals minus 0.2795. Now, that value of k we'll be using, so put that in memory. So the question, find the temperature of the body after a further 2 hours have elapsed. So then after a further 2 hours, that is when T equals 6, okay, given our last reference point was when T equals 4 hours, so another 2 hours, T equals 6. Putting that T equals 6 into our formula, we get T equals 18 plus 52 e to the 6k, and of course we're using that k value that we've just found, and that works out to be that T, the temperature, equals 28 degrees rounded to the nearest degree. Excellent. Well, that concludes the lesson. Good luck with your questions.